So this is Physics 105, Chapter 13, which is going to be very different from what we've just done. This is about fluids. What's a fluid? A fluid is something that flows. It's not just a liquid, it's a gas. So as far as we're concerned, a fluid is a liquid or a gas. So here we go. We're going to understand pressure in liquids and gases. We're not going to do this actually, sorry, forget about that one. We're going to use Archimedes' principle to calculate the buoyant force on an object and figure out if it's going to float or not. We'll use the equation of continuity to calculate flow rates. Maybe we're going to do this, but we're going to talk about how pressure varies with depth, but we're not going to talk about manometers and barometers, sorry. Okay, then we're going to learn about Bernoulli's equation. Bernoulli's equation. And then we're going to talk about viscosity and the flow of realistic fluids and apply Poiseuille's or something, the equation to viscous flow. Okay. All right, let's talk about pressure. Oh yeah, sorry, before we do pressure. So this is something that we're going to use all the time in this chapter. And you should know this from chemistry, right? So this is mass density, and physicists like using rho, the Greek letter rho. So the mass density is the mass divided by the volume. There's other types of density, you know. You can have area density, mass over area. You can have length density, mass over length. You can have charge density. There's all sorts of densities. So that's why you really got to say mass density, mass over volume. All right, so let's talk about pressure. Okay, pressure. So this is pressure for a small area. So pressure is F perp, the perpendicular force, divided by the area. It's a scalar. That's kind of weird, right? Because force is a vector. Force is a vector. But see, this is F perp. So here, this is a surface. This is the perpendicular component of that force that presses against the surface. Right? So basically, fluid pressure acts perpendicular, right? Fluid pressure acts perpendicular to any surface in the fluid, no matter how that surface is oriented. So, all right, so that's why we just say F perp, because the pressure always acts perpendicular to the surface, no matter how the surface is. So that's what I mean. So pressure, there's no intrinsic direction, it's just always perpendicular. Now, careful. The force due to fluid pressure also pushes against all parts of the fluid itself, right? So pressure exists within the fluid, okay? Everywhere within the fluid there's pressure. So you can think of pressure against a surface, then you can think of pressure everywhere within the fluid itself. All right, so let's look, all right, so there you go. So force divided by this cross-sectional area. So let's learn about pressure. Okay, so this is called a pressuring measuring device. It's kind of funny because it's just a spring with a little piston thing there, right? All right, so just pretend these things measure pressure, okay? All right, so this is just a lab. This is a beaker full of water, you know. So there is pressure at the bottom of the beaker only, at the bottom and the sides, or everywhere. So pause your video and figure it out. Okay, the answer is everywhere. I just told you that, right? There's pressure everywhere within the fluid, okay? So there's pressure everywhere in the fluid, not just at the bottom of the walls. All right, okay, so there's pressure at the surfaces, but there's also pressure within the fluid itself. Okay, the pressure at one point in the fluid depends on the orientation of the pressure measuring device. So pause your video and think about that. The answer is false, right? The pressure at one point in the fluid is the same. Remember? Because it's a scalar, it's not a vector. Whether you point the pressure measuring device up, down, or sideways, the fluid pushes up, down, and sideways with equal strength. Pressure is a scalar, okay? There's no direction to it, right? Because it's always F perp divided by the area. Oh yeah, okay, I'm just repeating myself. Pressure does not have a direction of its own. It can produce a force, F perp, which equals PA, right? Look, pressure is force over area. So therefore, force equals pressure times area. Okay. Okay, so pressure does not have a direction of its own. It can produce a force, F equals PA in any direction. Okay, any direction. All right. Now this is in a liquid. All right, so in a liquid, so just, think about your experiences in a pool or in the ocean or a lake or a pond or whatever. In a liquid, the pressure what? Increases with depth, decreases with depth, or is constant? So pause your video and think about it. All right, so hopefully you know from your experience that pressure increases with depth. In a liquid, right? In a liquid, the pressure increases with depth below the surface. Okay. Now how about a gas? Now we're just talking about a lab size. We're not talking about the atmosphere, you know what I mean? We're just talking about like a little beaker full of air, So in a gas, in a lab size container, the pressure does what? So pause your video and think about it. Get ready to vote. Okay, in a lab-sized container of gas, the pressure is the same. In a gas, the pressure is the same at all points, at least in a lab-sized container. Okay. All right. Now, oh boy. What we want to do, okay, so we know that in a liquid the pressure increases with depth below the surface. Well, what we want to do now is we want to figure out how. So basically we want to figure out an equation. Now, I'm not just going to give you this equation because I'm going to derive it. I'm going to show you how you figure it out. And the reason I'm doing that is because you'll learn a lot of things while I'm doing it that we're going to use later on. So this is just an awesome example. All right, so too much, right? Okay, so here, this is a beaker full of water. The water is not moving. And what we want to do is we just want to look at some water, okay? So just pretend we're just looking at this cylindrical piece of water. All right, so it's nothing, it's just water, right? There's not a real cylinder here, there's no side of a cylinder. We're just looking at this piece of water, okay? That's all. Let's see. So this piece of water, this here is the depth, and this is the cross-sectional area, okay, A, all right? Again, this is all in equilibrium. There's nothing, moving or anything like that. Okay, so let's go. So whatever is above the liquid pushes down on the top of the cylinder. So that's the atmospheric pressure. So we'll say the pressure P0 at the surface. So atmospheric pressure is pushing down. The liquid on each side of the cylinder pushes in, right? Right? And then, this is liquid. The liquid beneath the cylinder pushes up on the cylinder. So the pressure at the depth D is P, okay? So let's review that. So this here so we want the pressure here at depth D, we're going to call P, because that's the variable. The pressure up top let's call it P0, because that's just atmospheric. All right? Now, let's use some things that we learned a long time ago. We have all these forces, right? Because force equals pressure times area. So we have all these forces. So what do you do when you have a lot of forces? Force diagram. So let's draw the force diagram. Okay, so again, this is just this piece of water, right? This region, maybe it's better to say a region of water. Well, what's the forces acting on it? Well, gravity's pulling it down, so there's mg. Okay, remember, pressure is force over area, so force is pressure times area. So atmospheric pressure times the cross-sectional area, that's the force, P0A down, right? Then we have this pressure here times the cross-sectional area, so we have a force up. So there it is, okay? Now, wait a minute, what happened to these guys? Well, they cancel, all right? The forces on the sides of this region of water, they cancel. Now again, this is an equilibrium, right? So the net force equals 0. And you can see that this here has to be larger than this, right? Because, you know, here, this goes down, but we also have weight. So this plus this has to equal that, which basically says that this pressure has to be greater than that pressure, which we already knew, but I'm just saying, another way of looking at it. All right, so let's write it down. Let's do the Newton's second law. Okay, so the sum of the forces in the y direction equals 0. What does that imply? It means the up forces equal the down forces. So PA equals P0 plus mg. Great. Now, this is a liquid, you know. Most of the time, you don't really know what the mass is, right? I mean, who knows what the mass of this thing is? But what you generally know, like you know the depth, and you know the cross-sectional area, so you know the volume, okay? So that's nice. So, in other words, I don't want to put mass. So how are we going to get volume? Well, like I said earlier, the mass density equals mass times volume. Therefore, the mass equals the density times the volume. We're going to do that so often, you're going to be able to do it in your sleep. Okay, so now we're going to say that PA equals P0 plus rho VG. Okay, well that's cool. Now, this is wonderful, but remember, I'm trying to get an equation for how the pressure varies with the depth. Yeah? So I don't have any, the depth is D. I don't have a D in my equation. So what am I going to do? I got to get a D, right? Well, what's this volume? What's this volume thing? Well, you know, it's a cylinder, right? Cross-sectional area A, length D. So what's the volume? So the volume is just cross-sectional area A times D. Great! So I'm going to say PA equals P0 plus rho GAD. All right? I'm not done yet. Okay? Now, oh, wait a second. What did I do? You see what I forgot? I forgot an A here. Golly. Right? You have to have an A. It's a force, right? So, oh, golly. That's fine. Okay. Oh, that looks stupid. Okay. All right. Now, look at that. How can you simplify that? We have an A here, A here, A here. Let's divide by, let's get rid of the A's. So you have P equals P0 plus rho GD. That's the formula that we want, right? This is the big deal. Woo, okay? So that shows you that the pressure equals whatever's on top plus the density times G times the depth. So as the depth increases, the pressure increases, which is what we already knew, but it's not. There's the formula. Okay. All right. So the pressure at any depth equals the pressure on top, atmospheric or whatever. Doesn't have to be just atmospheric, could be a piston, you know, plus the density G depth. So this is a linear equation, right? The pressure varies linearly with depth. You increase the depth, you increase the pressure. It's a line, right? Okay. Now let's do a special case, which is this, right? The special case is when there's no piston here, it's just atmospheric pressure. So the special case is this P0, right? The surface of the liquid is open to the atmosphere, so P0 is just P atmosphere, okay? And I wrote it, what's the deal with this? I just wrote it like that just to say that the pressure is a function or depends on depth, okay? You don't have to write that if you want, but the pressure depends on depth. Now, we got to be careful. What do we mean by depth? I mean, you think it's simple. Well, hold your horses. Okay, here. So here, this is a lake or something, I don't know. And here's the question. The pressure at A, is it equal to the pressure at B? Now, why should that cause you to think? Well, A is directly under the water. B is underneath this cliff thing, right? So, are the pressures the same? In other words, is this depth the same as the depth for B? How is depth defined? Well, believe it or not, it's true, okay? Because all you care about, I don't care about if there's a cliff there. The point is, this forms a line, right? A and B, whatever, they form a horizontal line. And this is the depth. Even here, right? The depth would be considered a 5.5 meters. So there you go, all right? Both points are located at the same vertical distance of 5.5 meters beneath the surface of the water. So don't let this little cliff fool you, all right? I mean, here's another way to think of it. If this pressure were different than this pressure, what would happen to the water? It'd move around, right? You know, I mean, it would move around until it reached some state of equilibrium. So they have to be the same, you know, at the same distance. Okay. All right, here's another one. Okay, the pressure at A is equal to the pressure at B. Pause your video, figure it out, or think about it. And be careful, you know, this is open, this is closed. So I'm just trying to get at what that depth means. So the pressure at A is equal to pressure B. What do you think? It's true, okay? It's true. This is the open surface of water, and so this is the depth here, which is the same as here. So this pressure here would be exactly the same as that pressure there. Kind of interesting, huh? Okay, here, okay, we have all these weird tubes, you know. This is large diameter, that's small diameter. Here we get this bubble thing here. Here we get a corkscrew thing here. It's at some weird angle. But come on, here's the surface of the water, right? And all we care about is the vertical distance. I don't care about this goofiness, you know. All we care about is the vertical distance. So everywhere along this horizontal line, the pressure is the same. So that's kind of important, you know, horizontal line, pressures are the same. We're going to use that again and again. All right, so I'm beating this to death, right? What is the relationship between D1 and D2? So what we're saying is the pressures here are the same, correct? Well, that's what they're supposed to, you're supposed to know that, right? So the pressure here is the same as the pressure here. So what is that? What has to be true about D1 and D2? So pause your video and figure it out. Okay, I hope you understand by now that it has to be the same, right? Because the pressure varies with depth. And this is the same. They're the same, right? I mean, it's at the surface, you know, right? I mean, they're both at the surface, so this has to be the same distance. Okay, oh yeah. Now, so I actually did this demonstration. I would do this demonstration in the classroom, but it makes a real mess. I'm in the library with a carpeted floor, so I didn't want to make a mess. So this is it's called a graduated cylinder. It has holes in it. And so you fill it up with water, and remember, the pressure increases with depth. So you can have a lot of pressure here, not so much pressure here. Now let's say that the areas are the same, so you can have a lot of force here, not so much force here. So notice there's a lot of force here, so the water kind of really shoots out, you know. It's still a parabola, right? This is all free fall, but it really shoots out because there's a lot of force. Here, there's not so much force, so it's kind of, you know, right? So that's a great example of this equation, you know. A lot of pressure here, not so much pressure here. Big depth, little depth. All right, this is a tough question. So a U-shaped tube is open to the atmosphere on both ends. Yeah, you can see that. Water is poured in the tube, followed by oil. Now, oil floats on water because it's less dense than water. We'll talk about that later on. Okay, so the oil is floating on the water because it's less dense, right? Rho, you know. So which figure shows the correct equilibrium configuration? So pause your videos and figure it out. So the answer is C. The answer is C. Why? Well, you know, this is water, this is water. You draw the horizontal line, equal pressure, right? Now, why is there more oil? Why is there more oil here than water? Well, it's just this part. I mean, they're both open to the atmosphere. So this is atmospheric pressure, right? So we don't care about that. So just look at the rho g d. Okay, for the oil, the density is small. So that means that this is going to be large, right? That's all, right? The density of oil is less than that of water, but this thing has to be the same for both oil and water, so that means there's going to be more oil. I hope that makes sense. All right, let's talk about gases. What is the primary cause of pressure in a laboratory-sized container of gas? So pause your videos and think about that and vote. Okay, so what happens in a gas? What are those gas molecules doing? Are they just sitting there? No, they're moving around like crazy. And so the primary cause of pressure in a lab-sized container of gas is just molecular collisions, Now, I talked about atmospheric pressure. Atmospheric pressure at sea level. By the way, does that look familiar? I hope it looks familiar. If it doesn't, you're spending too much time in the library. Anyway, so, all right, so what is atmospheric pressure? So there's all sorts of units for pressure. It's kind of ridiculous. So atmospheric pressure, 1 atmosphere, okay, equals 101.3 kilopascals, which equals 14.7 pounds per square inch. Okay, by the way, I forgot to say something. Pressure, again, is force over area. Force is in newtons, area is in meters squared. That's called a Pascal, after Mr. Pascal. So the Pascal is the metric system unit for pressure. So that's what we'll use, unless the book says to do something otherwise, you know. So as far as we're concerned, atmospheric pressure is 101.3 kilopascals. Now, come on. 101.3 times 10 to the third pascals. That's basically 10 to the fifth pascals, right? So the way I look at it, I don't care about the 101.3. I'm just going to use 10 to the fifth and be happy. If you'd like to use 101.3 times 10 to the third, go right ahead. But I'm not going to bother. All right? Now remember, just use this equation. So atmospheric pressure can produce forces in any direction, right? Any direction. It's a scalar, right? Any direction. Here is a vacuum cleaner. How does a vacuum cleaner work? So let's say there's dust on the floor. Is there like some magic arm that grabs the dust and brings it back, into the vacuum cleaner? In other words, is the dirt sucked up into the vacuum cleaner? Well, no. All right. Why is it called a vacuum cleaner? I mean, we'll talk more about this later, but basically, you have a fan, right? A propeller blade, a fan blade, and you turn it on, all right? So you get so the air is moving really, really quickly inside the vacuum cleaner. What we're going to see later on is when the velocity of the air gets higher and higher, or larger and larger and larger, the pressure gets smaller. So what happens in a vacuum cleaner, you get this air moving really, 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 really fast. So the pressure in here gets really, really, really small. Well, you still have atmospheric pressure outside, right? So what happens is, you have the brush which kicks up the dirt, and then you have this large amount of atmospheric pressure on the outside, small pressure on the inside. So it's basically the atmospheric pressure pushes the dirt in the vacuum cleaner. So that's kind of how it works, all right? We'll talk more about that later. But it's kind of cool, The vacuum cleaner, the outside pressure is larger than the pressure inside it, so it pushes the dirt in the vacuum. The vacuum doesn't suck it up or something like that. If you have kids, this is a great invention. So little kids. So this is a suction cup on the bottom, because little kids always spill everything. And so this here, the bowl or whatever, is connected to the suction cup. You just put the suction cup on the table and it doesn't move. So that's totally awesome, right? Now, how do suction cups work? Well, if you have a suction cup and you push it on the table, basically there's almost no air underneath it. So you have atmospheric pressure pushing down on it, but there's no air underneath it, and so there's no atmospheric pressure underneath it. So it sticks, it's awesome. How come I can lift my finger? Well, because, there is really air underneath my finger, right? So there's atmospheric pressure all around the finger. Okay. All right. So the net force is basically zero, right? Because the atmospheric pressure is the same everywhere, so the force is zero. Here's a question for you. If the air pressure in a tire equals atmospheric pressure, what is the condition of the tire? So please pause your video and figure it out. Okay, you're back. The answer is flat, right? If the air pressure in the tire just equals atmospheric pressure, then it's flat, right? You want to exceed atmospheric pressure. So this is called a flat tire. You can see they're fixing their flat tire. So what is that got to do with anything? So here you have to be super careful. So absolute pressure equals atmospheric pressure plus gauge pressure. So when you have a bicycle tire, and it's flat, again, so you have absolute pressure equals atmospheric pressure. So you have to exceed atmospheric pressure, with a pump or CO2 cartridge or something like that. Now, you need to know this because sometimes they'll have a question, homework or exam, and they'll say, what's absolute pressure? And you have to remember to add atmospheric pressure. So just be really, really careful when you have a question dealing with pressure. Do they want gauge pressure or do they want absolute pressure? Okay, we'll do one long example, then we'll call it a day. So everybody read that. All right. How much force does the fluid exert right here? And then how much force does the fluid exert right there? Now notice, there's the water, or whatever it is. Oil, I guess. Oil, right? And so this is at a different depth, and this is at a different depth. And we want to know force. Force is related to pressure. We have different depths. So, what's the equation? It's just that equation that pressure varies linearly with depth. Okay? All right, so there we go. So the pressure at some depth equals the pressure on top plus rho g depth. Okay, wow. Let's figure out P0 first. Now look at, this is not, okay, it is open to the atmosphere, but there's a piston on it. You know, there's a piston on it. So the piston is exerting a downward pressure as well. So P0, it's atmospheric pressure, but it's also equal to that piston, P piston. Okay? Now, so we have P atmosphere. Okay, now what's the pressure of a piston? It's just the force divided by the cross-sectional area. So what's the force? Gravity, right? So mg, I gotta be careful, m piston, g, and then over the cross-sectional area. Okay, so what is that? Okay, again, I'm just going to be lazy, 10 to the 5th. 10 to the 5th pascals. And then, let's see, the mass of the piston's 10 kilograms. G is G. And they're always rotten, right? They always give you the diameter. You want the radius, you know? Oh, well. So pi r squared, right? So pi 0.02 meters squared. And I promise you, you do that, you get 1.78 times 10 to the 5th pascals. Okay, so that's the pressure, that's just P0, right? Okay, great. Now, what we want to do is we want to figure out A, right? We want to do A first. So A. Okay, so, you know, okay, so we got P0, we know rho, we know G, what's D? That's the question, right? What is D for this? Well, this is 60, this looks like it's half, so that's 30 and that's 30. This is 100, and remember, what's the depth? It's this, right? That's the depth. So, if this is 100, and this is 30, the depth is 70 centimeters. That's the key to the question, right? That's the key to the question. So for A, D is 70 centimeters, which is 0.7 meters. Okay, so therefore, rho GD, okay, rho is 900 kilograms per meters cubed. G is G. And D is 0.7 meters. So I promise you do that, you get 6174 pascals. So therefore, the pressure at A is P0, which is this, 1.78 times 10 to the 5th pascals, plus rho GD, which is this, plus 6174 pascals. And you do that, and you get basically 1.84 times 10 to the 5th pascals. That's pressure at point A. Okay. Now, wait a second. They didn't say what's the pressure. They said what's the force. Right? Ugh. Okay, no problem. So, force is pressure times area, right? So the pressure is that, 1.84 times 10 to the 5th pascals. And what's the cross-sectional area here? It's just pi r squared. So it's pi r squared, which I promise you equals 5786 newtons. So that is the answer to the question. Okay. Okay, B. How much force does a fluid exert at the end? Well, you know, I'm still going to use this equation. P0 is still P0, right? That doesn't change. What's the only difference? The only difference is now the depth is this. So this is 100 centimeters. This is 30 centimeters. So the depth is 130 centimeters, 1.3 meters. So it's basically the same problem, except instead of putting 0.7, you're going to put 1.3. So that's the only difference. And that is a good place to stop. Thank you.